We're going to be doing more work with exponents. Last time was just the beginning. And some of the exponents we ignored last time were ones that were negative or zero. So let's start with that one first. Remember that no matter what, if you have the same base, when you multiply two numbers to powers, you add the exponents. So this was one of the rules we've already had. I'll put a box around it. Hopefully you remember that rule. I think it's called the power rule or something like that. I'm not sure exactly what the name is. Let's address x to the 0. So what is x to the 0 equal to? Well, for this, I'm going to assume that x itself is not 0. So let me go ahead and show you what I have here. We'll start with x. Okay? X is the same as x to the first power. But that's the same as x to the first. 1 plus 0 is still 1. So what I'm going to do is make use of this rule up here, because now my m is a 1 and my n is a 0. So I can break this up into the following: x to the 1 times x to the 0. And so x to the 1 is no different from x. Here's what I have. X to the 1 is the same as x, and then x to the 0 was over there. On the left-hand side, I had just an x. Now, if I want to figure out what x to the 0 is, I'm going to get it alone on one side of the equation. So I'm going to divide both sides by x. On the left side, you know that x over x is 1, and on the right side, these x's cancel, and I'm left with x to the 0. So that's what we have. The rule is this: x to the 0 equals 1 when x is not equal to 0. So there's a rule. The rule of the 0 exponent, I don't even know what it's called. Let's just call it the 0 exponent rule. But you'll notice that it doesn't work when x is equal to 0. It only works when x is not 0. We do have a situation where we handle 0 to the 0 power. That's simply undefined. So you simply can't do 0 to the 0 power. Try on your calculator. You'll see it'll give you some sort of an error message. But let's just do a few examples to illustrate. There's really not a lot to illustrate with things to the 0 power, but as an example, I'll do some anyways. So take any number you want except for 0 and raise it to the 0 power, and you get 1. And I mean it. If I take a negative number to the 0 power, I still get 1. If I take some weird expression like this to the 0 power, I still get 1. So long as the stuff inside of the parentheses is not 0, I'm okay. So I would have to say something like this off to the side. If something like this, though, negative 4 to the 0, you've got to remember to do the exponent before you do the minus sign, because I could think of this as negative 1 times 4 to the 0. So you would do the 4 to the 0 first because exponents come before multiplication. 4 to the 0 is 1, and you can see that you end up with negative 1. What's the big deal? Well, the negative wasn't in parentheses, so that's how I was able to pull out this negative 1 here, is because the negative was not in parentheses. So hopefully you're getting the idea. If I do something like 5 times 3 to the 0, you would do the exponent first. 5 times 1 equals 5. I think that's all the examples that I have for now. Now let's handle negative exponents. So we'll start once again. All these rules, most of these rules are written so that the base is not equal to 0. Some you can, some you can't. It just depends on them. Whenever we see that we are going to run into trouble, I'll usually write x is not equal to 0. So what we have here is the following series of equations. I know that 1 is the same as x to the 0. Now take any or let's call it whole number, or a natural number. Let's do that. So you know that any number minus itself is equal to 0. Like, well, that's kind of sort of a weird thing to put up there right now. Not quite just yet. I'm going to rewrite the top as an n plus a negative n. And then I'm going to break this up using our rule for multiplication. So what I have then, let me put my 1 down here again. So what I'm going to do now is divide both sides by x to the nth power. And that way on the right they'll cancel out, and I'm left with this rule. So this is how we're going to work negative exponents here. You can see that on the left I have a positive exponent, but on the right I have a negative exponent. So just to use some examples, let's suppose they have 4 to the negative 1 power. Well, according to our rule that we just have, that's the same as 1 over 4 to the 1, which is 1/4. 5 to the negative 2 power is 1 over 5 squared, which equals 1 over 25. 2 to the negative 4 equals 1 over 2 to the 4th power, which is 1 over 16. Of course, you know, the games that we play are like this, negative 2 to the negative 4. How do you do that one? Well, remember that's negative 1 times 2 to the negative 4. So that's negative 1 times 1 over 2 to the 4th, which is just going to be negative 1 over 16. Let me develop some more rules while I'm at this. What if I have 1, this may look weird, but a divided by b times b divided by a. So the rule I'm making up here is neither one of these, a or b, can be equal to 0 because b is in the denominator here and a is in the denominator here, so they're obviously not allowed to be equal to 0. But what I'm going to do is I'm going to raise both sides to the nth power. Now, one of our rules said that we can break that expression up on the right-hand side into a divided by b to the n times b divided by a to the n. On the left, 1 to the n is still 1. So I just needed to take it to the nth power to get where I'm going here. Now, next thing what I'm going to do is I'm going to divide both sides by the following. That way the b over a can cancel, like so, and I will have a over b to the n equals 1 over b divided by a to the n. That's actually a useful equation to be having, but recall what we just showed up above is that if I had 1 over x to the n, that's the same as x to the negative n power. You make that n a little bit better. In fact, by trying to make it better, I made it worse. So let's do this. So we had that rule from before. And so this time, playing the role of x will be this quantity here. This b over a quantity will play the role of x. So the next thing I'm going to do is take that b over a and have it raised to the negative n. So there's our next rule. So you can see the important thing to see here is that the negative exponent is attached to the left. You have your b over a, but look what happens when you make it positive. The a and b switch. A is now on top and then b is on the bottom. So to do some examples to illustrate this, if I have, say, 1/8 to the negative 2 power, that's the same as 8 over 1 to the 2 power. And that's the same as 8 squared divided by 1 squared, which is 64. The 1 squared, of course, is just 1. If I do 2/5 to the negative 3rd power, according to this new rule, that's 5 halves to the positive 3rd power. And then use our rules from last time to write this as 5 to the 3rd over 2 to the 3rd. And you'll end up with 125, not just 125 over 8. Another quick example. Let's see what else we have here. 10/3 to the negative 2 equals 3 over 10 squared. And that's the same as 3 squared over 10 squared, which equals 9 over 100. And the negative shouldn't make much of a a negative in front of the numbers. This usually is what causes students a lot of problems. Let me show you what I'm talking about. I have negative 5 halves. All that is raised to the negative 3 power. Now, there's a variety of ways that you can handle this thing, but probably, let me think, perhaps it might be best just to do this. What students often do when they have this swap like I just did, notice I just flipped the 5 and the 2 to make it a 2 and the 5. The negative 1, if you will, the negative was not affected by this because this negative out here is like negative 1 times the number. This negative up here is with the exponent. They don't have really any connection other than if this were an even number, the negative would cancel or something like that. But let me write this out to show you more details. I'm going to change that negative to a negative 1 times 2 over 5. And all that's raised to the 3rd power. So according to the rule we had last time, this is negative 1 to the 3rd, 2 to the 3rd, over 5 to the 3rd. Negative 1 to the 3rd is still negative 1 because the power is odd. 2 to the 3rd is 8. 5 to the 3rd is 125. And our final answer is just negative 8 over 125. Of course, I think I already did. Let's do one more example of this. If I have negative 9 to the negative 2 in parentheses, this is the same as negative 1 times 9 over 1 to the negative 2. I'm not sure I want to do the negative 1 just yet. Let me leave it like this for now. And you know what else too? While I'm at it, I think I'm going to do this in a slightly different way than I thought. You can rewrite this as, since the negative 9 is in parentheses, I can do this. So that's a way to get rid of the negative exponent. Now, if you take a negative number and square it, it is positive. So it has more to do with the exponent being positive than anything else. With positive exponents, they destroy the negative. And with negative exponents, with odd exponents, they do not. So if I were to do the same thing over here, but I didn't put the negative in parentheses, then this is what you're going to have. Because it's like negative 1 times 9 to the negative 2. I would do the 9 to the negative 2 part first, which would give me this. And then the negative is not related to the exponent, because this -1 that's out front is not taken to any power. So this is -1 over 81. Now a few more examples to sort of illustrate this property. Let's try 5 to the -2 plus 2 to the -2. Now, before I do anything else, I want you to see something. Some students might think that you do this. You can combine them because they're both raised to the same power. Nothing could be further from the truth. I don't know how I want to put this, but this is completely wrong. It's not true. There is no rule like that. Instead, if I have to do this rule, 5 to the -2 plus 2 to the -2, I have no choice but to rewrite the 5 to the -2 as 1 over 25 and the 2 to the -2 as 1 over 2 squared, which is 4. So I have to do this, and then in order to add these two things, notice that the LCD equals 100. So I'll have to change my fractions both to being over 100 now. In order to change the 25 to 100, I had to multiply by 4. And in order to change the 4 to 100, I had to multiply by 25. And so when I add them together, 4 plus 25 over 100 is simply 29 over 100. Let's try another one. This one with a little more complication to it. Here I have 6 to the 0 minus 9 to the -1 plus 4 to the 0 plus 3 to the -2. Well, let me put down the value of each of these. 6 to the 0 we already know is 1. 1 over 9 to the 1 is, or 9 to the -1 is 1 over 9 to the first power. 4 to the 0 is 1. And 3 to the -2 is 1 over 3 squared. So let me do a little simplifying before I do anything else. 3 squared is 9, so I get plus 1/9 at the end. And notice that I have a -1/9 and a positive 1/9, so they can cancel, and I'm just left with 2. So that takes care of some of the rules of exponents. We're going to utilize all of the rules of exponents for this next section, which is section 2.2b. Now we're still going to be doing integer exponents. The exponents are whole numbers, positive or negative. But this time, the bases will be variable. And whenever you're dealing with a variable anything, you've got to be careful when it's allowed to equal 0 and when it's not allowed to equal 0. So for an example, one of the rules we know from earlier is this. It's clear that y cannot equal 0 when you do this, otherwise you'd be dividing by 0. So in the context of the problem, if we need to specify, we will. Usually what they'll want you to do for each of these examples, like this last one, and say I give you something like this, they might say this might be the directions. Rewrite with a positive exponent. That may be the instructions. Then you're given this. A to the -5 equals 1 over a to the 5. And that's all they expect you to do with it, because now the exponent is positive. The question is finished. What I'm going to do, I think I was going to write them all up, but I think maybe we'll do that. Let me write up a few of our rules here. x to the negative n is 1 over x to the n. And if I have then x to the n equals 1 over x to the negative n. I don't know if I did that one yet, but it's pretty simple to come up with that one. Let me show you. I will use the rule that I just wrote there. If you look at this rule, x to the negative n equals 1 over x to the n. What I'm going to do is I'm going to multiply both sides of the equation by x to the n. And that way, the left side I'm going to leave as it is. But the right side, both the x's cancel away, and we end up with 1. So now I can get the rule that I already had there on the right, but if I this time divide by negative n, then, well, actually, I don't know why I'm doing it, because I probably, no, it's okay. X to the n equals 1 over x to the negative n. So I hadn't done that one yet. What other rules are we going to use? We have x over y to the negative n equals y over x to the n. We have x to the n over y to the n equals, from this rule, x to the n equals 1 over x to the negative n. If I swap and put x in the bottom, the exponent is now negative. If I put the y up on top, its exponent will also be negative. So for most of the problems, we're going to be using these rules here. And I think another one we're going to be doing a lot of is this. If you do take something and raise it to a positive exponent, that's the same as x to the n over y to the n. So let's throw that on there as well. And that goes with this one. And I think, do we need any more? I did x to the m times x to the n equals x to the m plus n. And there was x to the 0 was equal to 1. So a whole bunch of rules here. You may want to put them on a note card and carry them with you wherever you go so that you can memorize these rules. But we're going to do, as you can imagine, we're going to do several examples to illustrate the use of these rules. I'll mention the rules at each time I think is necessary during the context of the examples I'm going to do. So if you want, you can print out, pause the screen and take a snapshot of it, or your textbook will always have the rules listed in them as well. So as an example, let me write down what they'll ask you to do. They'll say to rewrite using positive exponents. And in this example, we have h to the negative 2 equals k over k to the negative 1. So the rule I'm going to use with this, since they both have negative exponents, is I'm going to use this rule. X to the negative n over y to the negative n is y to the positive n over x to the positive n. So according to that rule, I'm going to have k to the 1 over h squared. So notice the k is on top now and the h is in the bottom. And you could leave that as your answer. That's perfectly correct. But if you ever were to look up the answer in the back of the textbook, it wouldn't write k to the first power. So there you go. And the next one will be the same. So this time we'll have v to the negative 2 divided by w to the negative 7. And that will end up being w to the 7th all over v squared. Now we're going to start mixing it up a little bit with the following. 9x to the negative 4 divided by y to the 5th. I think I'm going to do this one in detail, but then the rest of them after that I probably won't have to use as much details as this one. If I were to write this as 9 over y to the 5th times x to the negative 4 over 1, then you would know that this is equal to 9 over y to the 5th times 1 over x to the positive 4. And now when I multiply all this together, and I put it in alphabetical order, although that's not required, this is the answer you get. So the important part was this. Let me just write the one step that was crucial to this. It wasn't that I broke it up or anything like that. I don't expect you to do any of this kind of stuff. I was just trying to explain why I end up with the answer I did. What you can do, though, is this. Anything that already has a positive exponent, like the exponent on 9, if you doubt whether it's positive, it's actually a positive 1. Only the things with negative exponents change from numerator to denominator or from denominator to numerator. So this x to the negative 4, if I wanted to have a positive exponent, I will put it in the denominator, and this matches with what I did earlier. So you can do this in one step, so long as you know that negative exponents jump down to the denominator. Or if there were a negative in front of this 5, then it would have jumped up to the numerator. Let me do more examples. This is when it starts to get hairy for a lot of students, so you got to be on your game. Here, let's do 1/9 a to the negative 4 b to the 3rd. Now, to utilize what I just said, you might think of this as the following. In the numerator, I have a to the negative 4 b cubed over 9, because you could think of these both as being over 1. You might find that helpful. Now I'll use the idea that I just had in the last example, and I'll draw my fraction, but what I'll do is leave anything that has a positive exponent where it is. And the only thing I'll move is this a to the negative 4 will come to the denominator and be a to the positive 4. For my next example, let me see, I have 7r divided by 2t to the negative 9 u squared. I guess I should mention it, but I didn't. I think I did it at the beginning of this. As you scroll through all these problems, notice that whenever you have an x and a y in the denominator, they cannot be equal to 0. All of the exercises that you'll have to do will make mention of whether they can be 0 or not. And for any of these, you have to assume that all the variables are not 0, because they could all end up in the denominator somewhere. So in this problem right here, usually they would say all the variables are not 0, even though the b could have been. We just ignore the 0 possibilities altogether when we're doing these types of problems. So the point I'm making is you should know when and when not the numbers themselves are 0, or if they even can be. So for example, since I have a u and a t in the denominator, then neither u nor t could be equal to 0, but r could be. But anyways, what am I going to do? I'm going to leave everything where it is that already has a positive exponent. So the 7, the r, the 2, and the u squared already had positive exponents. The only thing without one was this t to the 9th power, and I will simply put it up here. And that's it. All we have to do is eradicate the negative exponents, and that's all your book is asking us to do. So keep that in mind. As I do all of these examples, the rule is or the directions are to write them without negative exponents, or to write them with only positive exponents. So we can certainly do that. Here is a to the negative 2. Then we have b to the negative 2, c to the negative 1. Even though I said b, I meant c. And leave things alone that already have positive exponents, but nothing here has a positive exponent outside of that 1, but that doesn't really do much one way or another. So all of these three things in the denominator are going to raise up. So a squared, b squared, c to the 1. And what's left down there is the number 1. Well, you can drop that. It's not going to be crucial. So I can write my answers a squared, b squared, and then just times c. c to the 1 is the same as c. For our next one, we have 3 over y, and that's being raised to the negative 4th power. So the rule I'm going to use this time is when I have x over y to the negative n, that's the same as y over x to the positive n. So what I'm going to do then is change this to y over 3 to the positive 4. And then I'll make use of the rule. The rule went like this: a over b to the n was a to the n divided by b to the n. So that rule will be used to make this y to the 4th over 3 to the 4th. And I do want to illustrate, or I want to remind you that this answer that I have right now is correct. You could circle that as your answer unless you were told to evaluate the 3 to the 4th. 3 to the 4th power is 81. So depending on what your instructor requires you to do, you've got to be cognizant of that. For my next one, as you can see, they're going to get more complicated as we go. I have w over 5v to the negative 3rd power. I'm going to change that as 5v over w, this time to the positive 3rd power. And now I can use the one rule. It's a combination of rules. You had this: a over b to the n was a to the n, b to the n. Then you had a over b to the n is a to the n divided by b to the n. So I'm going to use that, the combination of those two rules, to write the following: 5 to the 3rd, v to the 3rd, all over w to the 3rd. So you can see basically all it means is that you're taking every single thing that's inside of there to the 3rd power. 5 to the 3rd is equal to 125. And you can't put anything else for the letters because, well, we don't know what they are, so I can't evaluate them. I'll just have to leave them like that. That's a w raised to the 3rd power. So more complications. Let's see what we have next. I have 2tu over v, that's raised to the negative 6th power. So I'll be able to rewrite this as v over 2tu to the positive 6th power. Flipping it upside down does that. And now I will take everything inside to the 6th power. That's because it's either a product or a fraction that you're allowed to do that. So the 2 should have been taken to the 6th power. T should be taken to the 6th, and U should be taken to the 6th. Then this is not considered finished. Like I said, this answer is correct, but quite possibly your instructor will not consider this finished until you tell him or her, what 2 to the 6th is equal to. I happen to know that 2 to the 6th is equal to 64. So 2 to the 6th equals 64 is how I got to that last line. Here's another one, the likes of which we've had before. When you're doing something like this, you can see that the 5 is not affected. The -1 is not part of the exponent, so it might not be a bad idea to do this. Put a dot here so that you know that the -5 is separate from the x to the -3. Then that's like -5 times 1 over x to the 3rd. Here I use the rule that x to the -n is 1 over x to the n. But then if you think of the -5 as the 5 part as 5 over 1, then you'll end up with -5 over x to the 3rd. And the negative can literally be anywhere. It could be attached to the 5, it could be in the denominator, or it could be out front. And most likely when you see the answer, if you were to do this problem and look in the back of your book, they would almost certainly put the negative out front of the whole expression. Next one we have 3g to the -5. And this is exactly like the last problem. If I think of it as 3 times g to the -5, then you won't be confused with the 3 being attached to the exponent anyway. I'll get 3 times 1 over g to the 5th, and that will make the positive exponent. As before, if I think of it as 3 over 1, I'm going to get 3 over g to the 5th power, and that finishes it off. Another example, suppose we have -d to the -5. I sort of indicated that you should think of this as -1 times d to the -5. That way you won't mess up the negative or the negative with 1 with the exponent. And this is -1 times 1 over d to the 5th power. And then you can finish it off by simply writing -1 over d to the 5th power. For our next one, I have 1 over c raised to the -5th power. And I can change that to c over 1 to the 5th power. That's c to the 5th divided by 1 to the 5th, which is just c to the 5th over 1, which of course is the same as c to the 5th power. Notice that this is one of those places where your book would definitely tell you that c cannot equal 0, because when you get your answer at the end, it certainly looks like c was allowed to be equal to 0, but it's not. So you'd have to make some sort of a stipulation that makes understood that c is not equal to 0 for a situation like that. Another example, 7 times 1 over t to the -8. And I used it over there too, didn't I? I should have probably told you, if I have a over b to the -n, that's the same as b over a to the positive n. So that's exactly what I'm going to make use of right now. T over 1 to the 8th power. And then we get 7 times t to the 8th over 1 to the 8th. And the 1 to the 8th is just 1, so I'm just left with 7t to the 8th power. Now I want to make up a couple of examples just for more difficult practice. So something that you can possibly see looks like the following. Suppose I have 2 to the third, x to the negative 4, y squared, all over 5 to the negative 2, z to the negative 3, w. And all of that is raised to the negative 1 power. So this example aims to use a lot of rules at one time. The first thing I'm going to do is the following. I'm going to just turn it upside down inside of the parentheses, but I'm going to leave everything the same for now. I am warning you, don't try to do more than one rule at a time, or you're going to probably run into some issues. So now that exponent is 1. Anything to the first power is the same as itself, so I'm going to drop the 1 power. Okay, now in order to fix all these exponents to make them positive, I'm going to leave whatever's already positive alone. That means in the numerator I have a w, in the denominator I have 2 to the third and a y squared. All the rest of the numbers and variables, like this 5 to the negative 2 and such, have to change position. So the 5 to the negative 2 has to come down to the denominator to make it a positive 5 squared. The same thing happens with z to the negative 3. It has to change to the denominator to make it z to the positive 3. The x to the negative 4 will have to come up to the numerator to make it x to the positive 4. And this answer, as I mentioned, is correct. However, if you want to finish it off all of the way and tell me what the numbers are, well, let's go ahead and do that. 2 to the third power is 8. 5 squared is 25. And then we have z cubed, y squared. 8 times 25 is 200. And there you go. All of the exponents have been fixed, and it's now everything is raised to a positive exponent. Let me do some more examples. Here in this one, we'll do 10, let's do some other letters, a to the negative 2, b cubed, all over 75, c to the 5th, d to the negative 2, and all that's going to be raised to the negative 5 power. Well, let's see what we get there then. The first thing I'm going to do is flip it upside down. So I have 75, c to the 5th, d to the negative 2. I haven't addressed any of the negative exponents inside yet. 10, a to the negative 2, b to the third. And that will now be raised to the 5th power. Now let's fix the negatives of all the exponents inside before I do anything else. Since I'm raising everything to the 5th power, I'm going to hold off a minute and do some other stuff first. So anything that's already positive in the exponent, I'm going to leave where it is. So when I look through, I noticed that it was c to a positive 5. The d to the negative 2 will have to come down to the denominator and make that a d squared. The a to the negative 2 will have to come up into the numerator, and I can decrease the size of my division line. Now what I would do next is I still wouldn't take everything to the 5th power just yet. What I would do next is simplify the 10 into the 75. You'll notice 5 goes into 10 twice, and 5 goes into 75 15 times. Well, let's see what we get. Now I have a 15 c to the 5th a squared all over 2b cubed d squared, and all of that is raised to the 5th power. Now, finally, I'm going to take and raise everything to the 5th power. And all of those exponents, you multiply them out. Now the 15 to the 5th, I don't happen to know that off the top of my head, so I'm going to do that on my calculator. And, oh wow, look at that. 759,375. C to the 5th is c to the 25th. Remember, you multiply these exponents here. So I'll get c to the 25th, and then I'll get a to the 2 times 5 will be a to the 10th, divided by, in the denominator, 2 to the 5th is 32. B to the 3rd to the 5th is b to the 15th, and then c to the 2 to the 5th is, d to the 2 to the 5th is d to the 10th. Maybe one last example. Hopefully this is something you can look at and get it before I show how to work the problem. So let's throw a negative in here. Let's do 35, and then we're going to do x to the -1, z to the -3, y squared. Let's see how many other letters I can use. Let's do down in the denominator, let's do 70 x to the 3rd, y to the -4, and then z to the 5th, and all of that will be raised to the -3rd power. So let me flip everything upside down to at least get that power outside into a positive. I'll leave the negative. The negative doesn't change whether you turn the thing upside down or not. But inside I'm going to turn it upside down. 70 x to the 3rd, y to the -4, z to the 5th, all over 35 x to the -1, z to the -3, y squared, and that'll be raised to the +3rd power. Now before I do anything else, I'm going to move and change all my exponents from negative to positive. So what I'm going to do, anything that has a positive exponent, I'm going to leave alone. And anything with a negative exponent, I'm going to move. So this x to the -1, for example, that's down here, I'm going to bring it up top and make it x to the 1 up there. Z to the -3, I'm going to bring up top and make it z to the 3rd. And then, let's see what else. I've got my x and the z. This y to the -4 will come down. Let me put the y squared first, and accompany the y squared that's already down there. This is to the 3rd power. Let me simplify as much as possible. 35 goes into 70 twice. And I can make use of the rules where they have the same base. I can write this as x to the 4th power. Remember, you do x to the 3 plus 1. Same thing with the z's. You would do z to the 5 plus 3. And same thing with the y's. Y to the 2 plus 4. And all of that's still raised to the 3rd power. Let me add up my exponents. So I'll get 2x to the 4th, c to the 8th, all over y to the 6th. And that's raised to the 3rd power. And now I'll go ahead and take everything to the 3rd power, including that negative out front, which is really negative 1. This out here was a negative 1, so I'm putting it like to the 3rd power. Then I'll have 2 to the 3rd, y to the 4th to the 3rd, z to the 8th to the 3rd. All of that is divided by y to the 6th to the 3rd. I'm not sure why I put a y there. Let me take it out. Change that to an x. And you know what? The division bar does not have to go and include the negative. So just that far. Well, negative 1 to the 3rd is still negative 1. 2 to the 3rd is 8. X to the 4th to the 3rd is 12. You can multiply the 4 and the 3. Same thing goes with the 8 and the 3 on the z. You get z to the 24. All over y to the 18. And now I'll just change my negative 1 into a negative out front. There's more than one way to do one of these problems. That's one of the issues that arises here. Why am I showing you another way? Well, some of my students appreciate it. What I'm going to do is copy what I had from before. And I'm going to redo this problem, but in a slightly different way. Some of my students have been keen to do something like this. Take everything to the negative 3 first. That's out front. And then I'll have, now I think actually before I do that, let me do one thing, because I don't want to be taking 35 and 70 to the 3rd. Let me cancel this first. If you can simplify your numbers, always do that first. So now I'm going to take everything to the negative 3 power, and here's what we get. So what I did is the negative 3 got multiplied to each and every exponent. That's why you're seeing now all this stuff happening. X to the negative 1, but to the negative 3. If you take negative 1 times negative 3, you get a positive 3. Z to the negative 3 to the negative 3 is z to the positive 9. You can go through the rest of it to see. So what my students do is now, it's only now that they go and change where the numbers are or the variables are to handle the negative exponent. So that's what I'll do next. So anything with a negative exponent will go and change its position. For example, I have a negative 1 to the negative 3. I'll put it down in the denominator to give it a positive exponent. But the x to the 3rd and the y to the, or the z to the 9th can stay put because their exponents are already positive. Although the y to the negative 6 has to come below. Okay, so I've taken care of everything in the numerator. There were 4 items. I now have 4 items here. Now the 2 to the negative 3 can come up to the numerator and make it a 2 to the third. I'll put a dot to indicate multiplication. The x to the negative 9 can come up to the top and become x to the 9. And then the z to the negative 15 can come up top and become z to the 15. However, we've already got the y to the negative 6. The y to the 12th was already around the denominator. Now let me go ahead and evaluate what I can. Now to do the x's and the z's, I'm going to rewrite this numerator as 2 to the third, x to the third, x to the 9th. I'm putting my x's together because I'm going to combine them. I got the z to the 9th, z to the 15th. In the denominator, negative 1 to the third is just negative 1. Y, then I have the y to the 6th and y to the 12th. Now remember, what I'm going to do is add up all these things. And I did mention the negative, it doesn't matter where it occurs, so you can just simply put it out front and leave it be. The 2 to the third is equal to 8. Now when I do x to the third times x to the 9, remember you add the exponents to get x to the 12th. Add the exponents for the z to get z to the 24th. And then add the exponents for the y to get y to the 18th. And I can't stand it. I have to check myself to see if I actually got the same answer. X to the 12th, z to the 24th, y to the 18th. And that finishes the material for this particular section.